We're getting there. So now let's start to put some things together. So, a system graph. I had like a real strong accent in that. Graph. System graph. People told me when I was a kid that I had a British accent. I don't know why. That doesn't make any sense. Canadians used to tell me that, which is weird because they have more of a British accent than Americans do. Yeah, but then everybody else thinks that I'm like from the beach of California. Yeah. Yeah, I know. Okay, a system graph is a representation of a physical system as a set of interconnected linear graph elements. The construction of a system graph requires a number of engineering decisions. In general, we can use the following procedure. So there's a list that I did not make you guys write out because it was a lot. And I didn't want to write it out in class. All right. Define the system boundary and analyze the physical system to determine the essential features that must be included in the model, including especially what are the inputs, the outputs of interest, so what are the things that we care about in the system, what energy domains are involved, so is it a mechanical system, is it an electronic system, are there both? Later on we'll learn how to incorporate other types of energy domains as well. And required elements, so that's going to be sort of the definition of the system. Inputs, outputs, energy domains, and required elements. Form a schematic model of the physical system and establish a sign convention. Okay? Always got to do that sign convention. We learned how to do that last week on Friday. It's on the internet. Determine the necessary lumped parameter elements representing the system. So A, energy sources, B, energy storage, and C, energy dissipation. So those are our three types of lumped parameter elements that we've learned about so far. We're going to learn about a fourth type, which is transduction, so you can go between domains. But we'll learn more about that later. Oh yeah, that's where the fun stuff starts. Well, I don't know. This is all fun to me. Identify the across variables that define the linear graph nodes and draw a set of nodes. So we've kind of started drawing linear graphs already, so this is familiar, I think, to us. Determine the appropriate nodes for each lumped element and add each element to the graph. Select a set of sign conventions for the passive elements and draw the arrows on the graph. So we use a sign convention for the engineering diagram that we drew, and then now we're drawing a linear graph, and we're going to use the same sign convention as we used to draw the physical system. If you didn't use a sign convention when you drew the physical system, now is the time. You gotta decide what your sign convention is going to be. Okay. Finally, select the sign conventions for the source elements to be consistent with the physical model and add them to the graph. So step 7 is important for your sign convention. You have to make sure that if the positive terminal of your voltage source is connected to a certain node, then your sign convention can't have it the opposite. Sign convention has to be consistent with whatever is physically being modeled, right? If the force is actually pushing to the right, and it's a source, you have to put that in as to the right in your sign convention. Otherwise, you're going to come up with the wrong sign. Okay, steps 1 through 3 are hardest. A considerable physical insight is required, and often it is helpful to have experimental results to guide this process. It's fine to try to come up with a model without experimental data, but for many systems, you need that experimental data in order to really specify the details of the model. Otherwise, the model won't be very effective. Okay, mechanical translational systems. So let's model a cantilever beam with a mass affixed to its end. Okay. Oh crap! Boom. Thank you. That was a close one. The replay will show that it was pretty close. Ruling on the field was too slow, though. All right. So, here's the physical system. We've got a cantilever beam that has a mass on the end, and there's a force source here. So, maybe we stuck an unbalanced rotating piece of machinery on a shelf. That would be something that would perhaps be a physical system that might be modeled like this. Okay, has some mass, maybe it's at the end of the shelf, and maybe we want to find out how much vibration we're going to have, force coming into this base of this cantilever beam, for instance. That might be one thing we would do. Be interested to know. So let's draw a schematic. So this can be modeled as a lumped parameter mass, okay, M, and a lumped parameter spring, K. So this cantilever beam has some stiffness associated with it. We can model it as being a sort of spring-like element. It's also going to dissipate energy too, so we probably should have a damper there as well. But it's going to be probably light damping if it's a metal cantilever beam. They do dissipate some energy though. So, all right. So say we modeled it though. Maybe we said the damping was negligible, and we modeled it like this. So let's draw a linear graph of this system. How many nodes do we have? So I was gonna have ground, right? And so one other node? Yeah, so we've got and actually so each lumped mass element we assign its own node to because it has a distinct velocity, a mass with a distinct velocity. So the mass node, whenever we have a mass node, we talked about, let's just go ahead and draw the mass node going to ground because it's always going to go to ground, right? There's M. We can also draw in, so where does the spring element show up? Sorry? To the ground, yep. So it goes to the ground. We could have used our other sign convention to tell us, our sign convention rule that says drops in the direction from or in the direction of the coordinate arrow. So our coordinate arrow points down, so this would point down. And finally, we have a source, a force source. So here is, oh, I didn't label K. So here's our force source. And we have to get the sign right on this one, right? This is the one that the sign is really important with. So what is the direction of this force source? Up. So up. Why up? So because they're in the same direction. The coordinate arrow is pointed in the same direction as the force source. So therefore, since it's a through variable source, it points away from ground. Whew! All right, we got it.
And also, you would have to interpret that because it would be going down, because that would just be sucking life out of the node.
Sucking life out of the node. I mean, technically, so for instance, if the force source was pointed up, and the velocity source and the coordinate arrow was down, then this would be going in the opposite direction, right? Still would work.
But then would K go the opposite direction? Or?
K would still be the same. Yeah. So yeah, we do this so that we know, well, we have to make sure that this is consistent, just so that we have a consistent with our actual physical system model. The sign conventions on the other elements are, if you get those wrong, it's like not that big a deal. Your interpretation might be wrong, like, oh, this is in tension, there's actually in compression. That's kind of a bad mistake, but it's not like the end of the world. So, yes?
So like throwing your schematic, you're doing how like forces that affect the mass, right? So like if there was an arrow for K in the schematic, it would be going up.
If there was a what?
If there was an arrow for the K in the schematic, it would be pointing up, right? Like it would be whatever's acting on the mass.
So all this is saying is here's the direction that we're going to assume the force is going in. In reality, like Fs could be a sinusoid that goes like plus and minus, for instance. And if it was doing that, then the actual direction of the force, the spring force, is going to be, it's going to be in tension, then compression, then tension, then compression, which is fine. Actually, probably this is going to be just in compression all the time because the mass is going to be on it, but depends on how much force. So, yeah, it's the sign convention is there, just like when you guys drew free body diagrams. And depending on your professor, you assumed that all the forces were, like, for instance, in the positive x direction. So I know sometimes they don't teach you that. I personally always teach that all the forces are assumed to be going in the positive coordinate direction. And then if they come out negative, they're going the opposite direction of the coordinate system. So you always know what it is. So you don't have to always go back to your diagram and be like, which direction did I draw this arrow? But this is essentially the same as you can draw arrows like left and right and up and down in your free body diagram. And then when you get a negative number out, you have to go back and say, oh, okay, it's actually going the other way, right? So for all these passive elements, that's all you're doing. We come up with a convention so that it's easier for us to interpret. But it's not essential. You can always go back to the diagram and say, okay, this came out negative. That means that the force is actually going in the opposite direction of my arrow, which is fine. Okay. Rotational systems. We got this. Let's model the following system. So we got a motor, which we're going to get into more details on how to model the internal structure of a motor, but for now, let's just treat it as a velocity source. Let's say that we have a velocity controller on it, and then we just treat it like a velocity source. Set the velocity to anything we want, it'll do it. Okay? So there's our omega s, our source. Goes through a drag cup, couples it to a flywheel, and then there's a bearing with some damping associated with it. So, linear graph of this system. How many nodes? So we've always got ground, right? So we've got ground. How many distinct angular velocities are we going to model here? Two. So, well, I mean, two besides the reference, of course, right? So this input shaft is all going to be at one angular velocity. So we'll call that node A, and I'll label it here, A. And then B is going to be the flywheel and this shaft over here. So B. Now, B has associated with it a moment of inertia, right? Which is our A-type rotational energy storage element. So there's J. Always goes to ground. And then we have, as attached to A, we have the velocity source, right? Which We didn't. So we didn't assign a coordinate arrow direction, did we? So let's assign a coordinate arrow direction to be. Let's like put out an imaginary shaft here so we can just interpret this easier. We don't even have to. I don't want to overcomplicate things for no reason. We can just draw our nice arrow with the two tips there. So right hand rule. So which direction, so we have an angular velocity source, which is in a cross variable source, right? And it is in the direction or opposite the direction of this arrow? In the direction of it. So in a cross variable source, in the direction of the coordinate arrow, tells us that it has to go which way? Down. Nice. Omega S. And the way that I always remember this is that typically we draw the arrow, the coordinate arrow, since we can assign it however we want, right? Typically we draw in the direction of the source so that it's consistent. We don't have this negative sign that shows up. So if we always do that, then cross variable sources always point down to ground, and through variable sources always point away from ground. So as long as you do that, you can just keep that in mind. Okay. Whew. Velocity source. Then this drag cup thing happens. How should I draw that in here? Between which nodes? A and B. So this is B2. And then there's this bearing here. And that is attached to this shaft over here, which is associated with node B, right? So it goes where?
To ground.
To ground, yeah, from B to ground. This is B1. Awesome. So I'm going to give you guys lots of homework practice on these so that you can get a feel for them. It's the hardest part. The hardest part is really coming up with a graph from a system. That is really the hardest part. It's the part that requires the most interpretation. The rest of it is just firing off rules. I literally have, and I'll give it to you next semester, I literally have, maybe this semester, a script that is written so that if you hand it the equations, it gives you the full system model. Like, it's pretty easy. Yeah.
So for the last one, do you not put omega j in our omega?
So J is the flywheel.
Okay.
So omega J, it's not a source. It's just when I drew this, I just wanted to show you that this is the angular velocity of the flywheel here. It was sort of like extra information to mess you up. Not really. I don't know. I was trying to clarify, but yeah. Okay. So omega j, if you were to look at this graph, omega j would be the angular velocity drop there, right? That is omega j from this node to ground. Make sense? Okay. So electronic system. Let's model an alternating output voltage being filtered and powering an instrument. So say I've got a belt driving an alternator, and here's a circuit that's filtering out this, it's filtering this signal, and it's going to an instrument. Okay, so this filter has this schematic. We're gonna say this is a voltage source here, Vs, And this voltage source is driving this circuit, and we want to know, eventually we'll want to know what the load voltage is, the instrument load voltage. Notice that we modeled the instrument as a resistor, right? That's a pretty typical thing to do. Depends on the system whether or not you can do that. You could have a capacitive load or an inductive load, and then you need to put in like a capacitor, an inductor, etc. But oftentimes we can get away with just a resistive load. And we have our filter here. So this is how we've drawn our electronic diagram. And then a linear graph from that is ridiculously straightforward because it's practically another form of a linear graph. It's just looks a little different. So how many nodes do we have in addition to the ground? 3. One here, and one here. So this is all ground, right? And so let's draw in our 3 other nodes. 1, 2, 3. A voltage source is connected to this node, and our sign convention. Oh, we better do a sign convention, right? So let's say current is flowing that way and voltage is dropping that way. Current's flowing this way, current's flowing that way, and let's say that way. Okay? So therefore, our voltage source, its positive terminal has got to be up here. So it's got to drop to ground this way, right? That's Vs. L1 is going to connect nodes A and B, right? So I'll draw A, B, C, and D. So A to B is what element? L1. And which direction should it go based on these conventions that we drew? Yeah. And then B, node B, does it connect to ground through anything? Yeah, through the capacitor. Well, we don't typically dash. It's an A-type energy storage element, a capacitor. We don't typically dash the C because a capacitor doesn't have to connect to ground. So C1. L2 is going to connect these 2 nodes, right? And C2 is going to connect C to ground, and then the load is also going to connect C to ground. All right. What do you guys think? Yeah. It's like, you've come up with another way of doing a schematic that describes the system. So physical source modeling is something that I think we can go through in the last 5 minutes pretty easily.